In the last section, we spent some time talking about quadratic functions, or functions of degree 2. In this section, I want to talk a little bit more about polynomial functions, but now of a higher degree. So let's say degree 3, 4, 5, and beyond. A few more notes on polynomial functions. Polynomial functions are continuous, meaning that there are no breaks like piecewise functions might have. And polynomial functions have graphs with smooth, rounded curves, unlike absolute value functions that have graphs with really sharp turns. And so what I've done here is I've graphed three things for you. Here I've got a cubic function. Here I've got in the middle a quartic function. So this is degree 3. This one is degree 4. And then we've got a quintic function, which is degree 5. So you can really see as we go up in degree how kind of wild these can look. And here are the general forms of these different functions. Of course, we've got a constant is just f of x equals a linear we know as mx plus b, quadratic ax squared plus bx plus c, but now we've got cubic, quartic, quintic, and so forth, all rising up, and they get a little bit longer here, all the way to the nth degree, we say. So the nth degree is a sub n x to the n. So here we're saying n is the power on x. The highest power on x is going to be that degree. Well, polynomial functions that have the simplest graphs are monomials of the form f of x equals x to the n. So they don't have to be as long as this, but this, of course, is just the general form. This is where n is the integer, is an integer greater than 0. And in these cases, the greater the value of n, the flatter the graph near the origin. When n is even, the graph is similar to that of x squared, and it touches the x-axis at the x-intercept. When n is odd, the graph is similar to x cubed. This, of course, is just considering these more basic functions. As you add more transformations to this, of course, it'll change a little bit more. So let's talk about the cubic function. It looks something like this. Some students kind of refer to this as looking kind of like a snake with a little bend here. And these are some more examples of how they might look. So in all three of these graphs, I've done the parent function in red. That's just f of x equals x to the third. And this blue one is negative x to the third. What do we notice? Well, we've got a reflection here. This is going to be a vertical reflection. So what was down here is now going to be up here. What was up here is now going to be reflected downward. This green one in the middle is x to the third plus 1, which means that we've taken every single point on my parent function and we've just shifted them up 1 unit. So we've translated this up 1 unit. And here x minus 1 parentheses to the third power. This is bringing everything to the right 1 unit. The standard form here is f of x equals a times x minus h to the third, and then plus k. But how do we know how it's going to look without necessarily graphing it? Well, one of the tools that we use is the leading coefficient test. And it says, note all graphs either rise or fall without bound. To determine whether the polynomial eventually rises or falls, we use this test, the leading coefficient test. This will look at whether the degree is even or odd, and whether the leading coefficient is greater or lesser than 0. So when n is odd, this means when the highest power is odd. This is x to the third, x to the fifth, x to the seventh, x to the ninth, and so forth. If the leading coefficient is positive, meaning that I've got maybe 3x to the third, or 3x to the fifth, or 3x to the seventh. Okay, when the leading coefficient, that 3, is positive, then we fall to the left and we rise to the right. Or in more technical terms, we would say as x approaches negative infinity, f of x approaches negative infinity. And as x approaches positive infinity, f of x approaches positive infinity. But when n is odd and the leading coefficient is negative, as an example, let's say I've got negative 2x to the third or negative 5x to the ninth. Okay, if that number in front of that x to the highest power, that degree, is a negative, then it flips a little bit. It'll rise to the left and fall to the right. Or in more technical terms, as x approaches negative infinity, f of x approaches positive infinity. And as x approaches positive infinity, f of x approaches negative infinity. So again, n is odd, positive, we go down to the left, up to the right. When n is odd, but the leading coefficient is negative, we go up to the left and down to the right. Now, when n is even, both the left and the right side follow the same pattern. They both either go up, so we go up to the left, up to the right, or we could say rise, rise, or they both fall. So we fall to the left here and we fall to the right. How we know is based again on the leading coefficient. So if n is even and the leading coefficient is positive, so this is maybe 5x squared, 5x to the fourth. Okay, that 5 is positive. Then both the left and the right side are going to rise. They both go up. So as x approaches negative infinity, f of x approaches positive infinity. As x approaches positive infinity, f of x approaches positive infinity. If n is even and the leading coefficient is negative, then the graph falls to the left and the right. So this would be maybe negative 7x to the eighth. Okay, so n is 8, so even, but we've got a negative in front of it for a coefficient. So that means that the left side would fall, the right side would fall. As x approaches negative infinity, f of x approaches negative infinity. As x approaches positive infinity, f of x approaches negative infinity. But note that the leading coefficient test only determines the n behavior on the left and the right side of the graphs, not the portions between. So while we know ultimately this will maybe go up to the left and down to the right, we don't know anything about what's happening inside those 2 points, what's happening between those two. So we needed some other tools. One of which is finding the zeros. If I know that it's going to rise to the left and fall to the right, and where the zeros are, I can get a better idea of what the graph is going to look like without necessarily having to rely on a graphing utility. So let's see what this says. Zeros of polynomial functions. For a polynomial f of degree n, the following are true. Number 1. The function f has at most n real zeros. So if this is x to the third, there are at most 3 real zeros. If this is x to the eighth, then the graph might have at most 8 real zeros, but it could have less than that. The graph of f has at most n minus 1 relative extrema. So these might be minima or maxima, minimums and maximum points. What that is saying is if this is x to the eighth, then I might have 7 of these extrema at most, but I could have less. How do I necessarily know that? Well, when a zero's factor has an even power or even multiplicity, the graph will bounce at this 0, thus cutting away one of these extrema. Okay, it might be even more than that if that factor is, to the 4th power or so. The same is true, could be true for odd powers. If it's just maybe, x minus 2 is a factor, then we've just got the 1, 0, and it's going to cross at this 0. But if it's that same factor to the third, let's say, then there's going to be less of these extrema happening because we're repeating that 0. And finally, I've got in the middle here, a 0 of a function f is a number x for which f of x equals 0. Okay, so let's do our first example here. It says, find all zeros and their multiplicity of f of x equals x to the third minus x squared minus 2x. Okay, first thing I'm going to do is set this equal to 0 because I want to find where this hits the x-axis. That's going to be when y equals 0. So x to the third minus x squared minus 2x. Let's set this equal to 0. And then I'm going to remove any common factors. So what can I factor out of all three of these terms? Well, they all have an x in common. So let's do that. I'm going to factor an x out to the front. And I'll be left with x squared minus x minus 2. And this is equal to 0. And I can factor this. Okay, I can factor this. I know that this x is going to stay outside. And x squared minus x minus 2, this will factor to, let's see, x squared. So we've got x here and x here. And then minus 2 plus 1. When I multiply x minus 2 and x plus 1, that'll get me back x squared minus x minus 2. So I'm just kind of doing the opposite of that. This is equal to 0. All right, so these are my factors. I've got x as a factor, x minus 2 is a factor, and x plus 1 is a factor. Zero product property says if all three of these things are being multiplied together and they equal 0, it must be true that at least one of these is 0. So now I'm going to set each of these equal to 0 and solve for x. So x equals 0, x minus 2 equals 0, x plus 1 equals 0. Well, this is already solved for us, and this only had a power of 1. Each of these is power of 1 here, power of 1 here, power of 1 here. So this x equals 0 is a 0 of whatever function this is, f of x, and it's got a multiplicity of 1. X minus 2 equals 0. So if I solve for this, I would add 2 to both sides. And I get x equals 2 is my 0. And this x minus 2 factor was to the power of 1. So I've got multiplicity 1 here. X plus 1 equals 0. Let's solve. Subtract 1 from both sides. So x equals negative 1. Again, this came from the factor x plus 1, power of 1. So my multiplicity is 1 here as well. Okay, let's do another one where maybe not everything has a multiplicity of 1. Let's find all the zeros and their multiplicity of f of x equals negative 2x to the fourth plus 2x squared. Again, I'm finding zeros, so this is when this is going to hit the x-axis, y equals 0 then. So I'm going to just set this equal to 0. Negative 2x to the fourth plus 2x squared. This is equal to 0. And let's factor out anything that we've got in common. I know I can factor out a 2. I'm going to make this a negative 2 that I'm going to take out so that my leading power is positive. So I'm going to factor out a negative 2. And I can also take out x squared because this is x to the fourth power and this is x squared. So the greatest that they have in common is x squared. This will leave me with, let's see, -2 divided by -2. That's just going to be 1. And then x to the 4th divided by x squared. So I've got x squared left here. And then 2x squared divided by -2x squared minus 1. Okay, and this is still equal to 0. All right, so here are my, here I can factor x squared minus 1. This is a difference of squares. So this will factor to x plus 1, x minus 1. And I've still got -2x squared here. And these are my zeros. So -2x squared, x plus 1, x minus 1. Really, this is just a coefficient on my x squared, and then this is to the power of 2 here. Okay, so what does this mean? Let's set each of these equal to 0. And we'll solve. If -2x squared equals 0, well, if I divide both sides by -2, I'll get x squared equals 0. And let's bring this all the way over here. X squared equals 0. Take the square root of both sides. This is my factor, by the way, here. Then I'm going to have just x equals 0. But because this had a power of 2 on it, as a factor, I know I've got a multiplicity of 2. We'll talk about what that means in a moment. X plus 1 equals 0. I'm going to subtract 1 from both sides. This will give me x equals -1. This had just a multiplicity of 1, because I've got a power of 1 here, power of 1 on this one as well. And then x minus 1 equals 0. Let's add 1 to both sides. I've got x equals +1. And this has a multiplicity of 1. Okay, what does this mean? Let's go back to this first example. I've got a multiplicity of 1 on the 0, x equals 0. I've got a multiplicity of 1 on the 0, x equals 2. And I've got a multiplicity of 1 on x equals -1. So this tells me that since all of these have an odd multiplicity, the graph will cross at these zeros. We could have something... Okay, we could have something that looks like this. At 0, I know I've got a point here. At 2, I've got a point here. And at -1, I've got a point here. And since this is n is 3, it's odd, and this is positive, I know that this is going to be falling to the left, rising to the right. It could look something like this. It might not be exactly this. I might have to test a few more points out to find out exactly what this looks like, but this gives me a good idea at least. Whereas if any of these had a multiplicity that was even, instead of crossing at these zeros, it would bounce. So down here, I've got x equals 0 is a multiplicity 2, x equals -1 has a multiplicity of 1, x equals 1 has a multiplicity of 1. So when I go to graph something like this, I know my highest power is 4, which means that both the left and the right side will either both rise or they will both fall. How do I know? The leading coefficient test, -2 at the front, tells me that This will fall to the left, this will fall to the right. Now let's take a look at my zeros. Well, x equals 0, so I'm going to put a point there. X equals -1, so maybe right here. And x equals +1, maybe right here. At -1, the multiplicity is odd, meaning it's going to cross. So it's going to cross this. Okay, maybe I made this a little bit too wide. Let's do something like this. It's going to cross here, and then it will come back down to this 0, but it's going to bounce because the multiplicity is even. So we're going to bounce off this 0 like so, and maybe this one goes higher like this, I don't know. And then it's going to come back down to this 0 at 1, which this multiplicity is odd, telling me it's going to cross here. So I'm going to cross and then come back down. So these are really powerful tools. This allows me to find the end behavior on the left and the right side, as well as where zeros are and how those zeros are going to behave. It gives me a really good idea of how to graph these things, again, without needing a graphing calculator or using a tool like Desmos. The last thing I want to talk about is finding a polynomial function when you're given some zeros. So as an example, I've got find a polynomial function with zeros 3, 2, and -1/2. Okay, so what does this mean? If I'm given the zeros of a polynomial function, you can find the equation for a polynomial function by multiplying the factors. So if my 0 is 3, x equals 3 is what this means. And my 0 is 2 here, x equals 2, and x equals -1/2. That means that my zeros, finding this, setting it equal to 0, or getting it equal to 0, that means that x minus 3 equals 0. So this x minus 3 is a factor. X equals 2, so this means x minus 2 equals 0. So x minus 2 is a factor. X equals -1/2, so if I add 1/2 to both sides, x plus 1/2 would be equal to 0. So x plus 1/2 is a factor. Okay, if you don't want a fraction here, then something you could do is let's multiply everything by 2. So let's multiply the left side here by 2. And we can multiply the right side by 2. And let's see what's going to happen. This is going to be 2x plus 1, because the 2 times the 1 is going to make 2 over 2. And of course, 0 times 2 is 0. So I could say 2x plus 1 equals 0, so my factor would be 2x plus 1. All right, these are my factors, x minus 3, x minus 2, and 2x plus 1. And it says here, if I can multiply my factors together, I will get the function itself. So what that's asking me to do is take x minus 3, multiply that to x minus 2, take that and multiply that to 2x plus 1. Okay, well, we can start with any two of these. We're going to be using a lot of boxes here. So let's start with x minus 2 times 2x plus 1. Let's go over here. I'll make a nice box. And we'll do x minus 2 along the top and 2x plus 1 down the side. This is 2x squared. -2 times 2x, that's going to make -4x. 1 times x, so plus x. And 1 times -2, minus 2. So this is 2x squared, combined like terms, minus 3x, minus 2. And so I can take this and come back over here and say, this was originally x minus 3 times x minus 2 times 2x plus 1. I found that x minus 2 times 2x plus 1 over here is this 2x squared minus 3x minus 2. So this is now x minus 3 times 2x squared minus 3x minus 2. Okay, and then I can do another box to multiply these together. Okay, this time it's going to be a 2 by 3 because I've got x minus 3 as a binomial, and then 2x squared minus 3x minus 2. This is a trinomial. All right, so now let's multiply. We've got x times 2x squared. This is going to make 2x to the third. X times negative 3x, negative 3x squared. X times negative 2, negative 2x. Okay, down here, negative 3 times 2x squared is negative 6x squared. Negative 3 times negative 3x is going to be a positive 9x. And then negative 3 times negative 2 is going to be positive 6. Okay, combining like terms here. I've got 2x to the third. I've got two terms with x squared here. So I've got negative 6 plus negative 3. So this is going to make negative 9x squared. 9x and negative 2x are going to combine to make positive 7x. And lastly, just plus 6 at the end. So this is my polynomial function with those three factors. Hopefully that gives you a good idea of how to find these graphs of different polynomial functions based on the leading coefficient test, as well as finding zeros and their multiplicities, so knowing when to cross a zero and when to bounce off the x-axis for a zero, as well as, given the factors, how to then find the function itself.